The semiconductor industry continues to evolve at a rapid pace, and with each new generation of technologies, there is the need to provide analytical support for these technologies, right from their original inception, right through to manufacturing to failure analysis. So what I'm going to talk about briefly is the applications of scanning probe microscopy analysis and how they can be applied. Some of the different SPM methods can be applied for advanced semiconductor analysis. And I am going to go through a number of examples rather quickly. So for more detail on some of the examples that I discuss, you'll see references at the bottom of a number of pages, and I would encourage you to follow up by reviewing those references for more detailed information. So for today's talk, first I'm going to discuss SPM techniques, some of the techniques that have good applications for semiconductor analysis. And I'm going to talk about the actual application. I'm then going to proceed and give a bunch of application examples, examples where we've used some of these methods in successfully completing semiconductor device analysis, even on some state-of-the-art devices. And then I'll finish up with some concluding remarks. So the techniques that lend themselves very well for semiconductor analysis are atomic force microscopy, scanning Kelvin probe microscopy, scanning capacitance microscopy, and scanning capacitance spectroscopy. With regard to AFM for topographic analysis, AFM can be used for high-resolution topographic analysis, and it can be used anywhere from incumbing polished wafers to deposited or grown films for making an assessment of deposited or grown films during the fabrication process. Also, structure metrology or physical analysis, actually performing dimensional analysis, especially at silicon level, to ensure that structures are their appropriate sizes. And then AFM also lends itself well to looking at physical defects, which might be invisible to various electron microscopy techniques. With regard to scanning Kelvin probe microscopy, scanning Kelvin probe microscopy can routinely be used for dopant profiling, for looking at films, either film integrity or film contaminant films. And also, we've done some work, we've successfully imaged disruptions in the silicon lattice based on the work function difference. With regard to because those are routinely used in conjunction with each other. And these as well would be used for dopant profiling and looking at devices, with regard to dopant profiling or other information in a plan view or cross-sectional analysis to disclose information with regard to dopant and dopant distributions in individual devices. Let's talk about atomic force microscopy. First, what I'm showing here is just a overview of the AFM technique. I'm not really going to spend any time on this. This is there for your reference to look at after the talk. So let's go right into an example here. In this example, what I'm showing is a sample. It's a semiconductor sample that has been deprocessed to the silicon level. So in other words, it's been chemically delayered, exposing the silicon and structures that have been formed in the silicon layer. And everything on these devices look normal. When I say everything, we want to look at the relevant features. Probably most importantly is the device channel. And then along with that, we have a spacer imprint on either side of the area where the polysilicon once resided. And then we've got the source and drain areas, highly doped silicided source and drain areas, which provide contact to the device. And when I look at these devices, what I'm looking for is line with uniformity in the polysilicon, good spacer formation, good silicide formation, and suffice it to say that everything in this particular field of view looks normal. So this is where we use high resolution AFM to gain a good understanding of some of the front end line processing and to see that everything is done correctly. Slip lines have become a problem really prevalent, especially with silicon on insulator technology. Slip lines being dislocations which may extend on the order of microns up to millimeters in the silicon. And you can see in this optical microwave evidence of slip lines. And we've used AFM to get a better idea of what these slip lines look like. And what I'm looking at, we've got a three-dimensional rendition here of some of the slip lines. And what we're looking at, just to give you a feel for the scale, is from here to here is roughly 1 atomic plane in the silicon. So slip lines, if they fall into the wrong location, can be detrimental to the function of a device or chip. AFM lends itself well to providing good analytical data on slip lines. Let's talk a little bit about scanning Kelvin probe microscopy and how that's used for advanced semiconductor analysis. Here again is a description of how the technique works, and I'm not really going to spend any time on this other than to say that the SKPM image is representative of the work function difference between the tip and the sample. Here's an example of some SRAM cells. These are NFETs, and again, this has been deprocessed to silicon. And what I'm pointing out is the relevant features here. Here's the device NFET channel, and these are the source and drain areas. And in and around this, this ring, we have trench isolation. If we look at the Kelvin image, we can clearly see the P-type silicon areas well-defined, showing up as bright areas in terms of the contrast, and the N-type areas showing up as dark contrast. Well, this came out of an analysis that we had done a few years ago. And when I was looking at the data in terms of the dopant profile information, what we can see, I found a little anomaly down here. We can see this dark region in the channels, indicating that we've got a slightly higher N concentration in those channels. And we were able to trace that back to a contaminant film early in the process, which did some attenuation of early dopant implants in this area, resulting in this dopant anomaly, leading to an inoperative device. Another example of scanning Kelvin probe microscopy is where we've successfully used it to image stress lines in silicon. What I've done here is I've taken a piece of silicon and I stressed it. I basically just took a piece of silicon and laid it over a paper clip on the table and pushed on it on both sides to flex it. And you can see what I've actually done is I've caused a fracture in the topography image here. But when we look at the Kelvin image, we see a whole array of different lines, very straight lines going in various directions. And I believe what we're seeing there is the image of the stress that I've created in the silicon, have caused minor disruptions in the lattice, which show up as a work function difference in our Kelvin image. So another potential application for scanning Kelvin probe microscopy is to image the results of stress in silicon. One of the workhorse techniques that we've used in semiconductor analysis, especially advanced device analysis, is scanning capacitance microscopy in conjunction with scanning capacitance spectroscopy. Here's a overview of how the SCM technique works, but we're really going to spend more time talking about scanning capacitance spectroscopy, in which we apply a DC bias. And that DC bias is applied uniformly throughout the sample, and it effectively forces the sample surface into varying levels of accumulation and depletion. And that's where we're sensing, that's where we're collecting our data right at the surface. What we found is that SCS highlights dopant-related phenomena which might not be otherwise detected under a single bias condition, and I'm going to show you an example of that right here. In this example, what we're looking at is 3 NFETs in cross-section, and at 0 volt bias, we see 3 NFETs. Here's our channels right here, source and drain areas, and they all look somewhat similar. Now, when I take the bias in one direction, I take it into -1 volt DC applied up through the sample. What I've done is I've forced the channels into inversion. All 3 devices, the channels, the P-type channels, have been inverted to N-type, and this is what would happen, if the devices were in normal operation. Now, when we take the bias conditions in the other direction to a +1 volt DC, I'm starting to accumulate the channels here, but we really don't see a dramatic difference until we go to 1.5 volt DC. And now you can see there's clearly a difference between the 3 devices. These two channels here, the relative concentration of boron in the channels is somewhat higher than this channel here. Well, it turns out that this particular device was turning on too early. And using the spectroscopic analysis, we were able to get a good understanding of why this device was turning on too early. The channel doping was too low. Let's talk about three-dimensional devices, state-of-the-art devices, the Finfet. So now we've got the gate that has totally wrapped around this fin of silicon, and current flow is actually in this direction here. And I'm going to show you how we've used scanning capacitance, microscopy, and spectroscopy on Finfet devices to actually find a fail that was pointed out on a single device. So what we're looking at here is the scanning capacitance microscopy image of an inverter, an NFET and its corresponding PFET, each consisting of three fins, three fingers. And what we're looking at is the channel doping. And one thing to keep in mind is dimensionally, these are only 14 nanometers across. So really, we're looking at 26 atomic planes across. It's actually quite remarkable that we're able to resolve this scale. And when we looked at these two devices, something peculiar showed up right away over on the PFETs. We found this site, which I'm calling the defect site. Now, what is that defect site? Well, we speculate that it's an area of higher concentration, but we used scanning capacitance spectroscopy to get a good understanding of that device. So what we've done here, we're looking at our 0-volt image that I showed on the previous page, and there's our little defect site. And now when we take it to successively higher voltages, what we see is the area around the defect site is disappearing, but that defect site is still slightly visible. And that tells us essentially that the dopant concentration there was slightly higher, leading to a leakage path in that device, which caused the device to be inoperative. Well, I mean, it was functionally okay, but it leaked. It was a sub-threshold leakage. And just another thing I want to point out is when we take these devices in different directions, so I'm adding a positive bias, and we look at our PFETs, we can see the PFET channels slowly invert. So this would be simulating the device the PFETs being turned on. And if we go in the other direction, we can, take a look at our NFETs, and we can see the channels start to invert there. And up here, we see what it would look like if the device was turned on. So that's a good application of scanning capacitance spectroscopy and how it allowed us to find an individual called out device, analyze that individual fin and find a failure mechanism. So with that, just want to go to some concluding remarks. And I want to say that scanning probe microscopy analysis has provided critical data in support from the technology, right from the beginning of the technology, its early development stages, all the way through to failure analysis. And it has also proven itself invaluable in the analysis of state-of-the-art three-dimensional technologies. With that, I'll conclude, and I thank you for your attention.